All right, so welcome to my talk. If you don't know by now, my name is Patrick. I am the creator of Objective-C and also a co-founder of Digita Security. So first up, let's get to know our target, what we're going to be attacking today. And Apple actually does a really good job explaining this. So we're going to watch a short clip from the WWDC keynote from last year, which explains this. So let me first figure out how to turn up the audio on my computer, because I don't have audio out. So go back to this. Come on, mouse. We're going to do this the old school way.
Next, I'd like to talk about security and privacy. You know, one of the reasons that people choose Apple products is because of our commitment to security and privacy. And we believe that your private data should remain private, not because you've done something wrong or because you have something to hide, but because there can be a lot of sensitive data on your devices, and we think you should be in control of who sees it. Now, to begin, we protect your information on your devices using state-of-the-art hardware and software. And this year, we're adding greater protections about how apps can access that information. Today, Apple devices check in with you before granting an app access to information like your location. You can tell because you'll see an alert just like this one. And macOS already provides API-level protections for things like contacts, photos, calendar, and reminders. But now in Mojave, we're extending these protections to include your camera and your microphone, as well as protecting sensitive parts of your file system, like your mail database, your message history, and your backups. And all of this is protected by default for any app that you run on the system. Important protection.
We make great videos. So. Okay, so we're not just here to obviously watch clips of Apple's keynotes, even though they are produced very well. So what we're going to do is we're going to break macOS via synthetic or programmatic clicks. So first we'll look at specific parts of macOS that we can target and ideally bypass, including the new privacy protections that Apple touted in Mojave. We'll then briefly highlight some previous attacks that utilized synthetic or programmatic clicks, as well as show Apple's defenses and patches. And then finally, we'll talk about a zero-day vulnerability that allows us to generate invisible synthetic clicks to interact with any component of UI and bypass pretty much everything. So first, what should we or what can we break if we have the ability to programmatically interact or synthetically interact with the UI? So I mentioned on Mojave, most sensitive actions now require explicit user approval. So imagine a hacker has gained access to a Mac system using any of the myriad of features that were talked about previously, social engineering, fake flash installers, zeros. So they've gotten code execution on a Mac. Now, obviously, they want to do things like perhaps load a kernel extension, run an Apple script, access the user's geolocation, access their photos. All of these actions now require explicit user interaction. So what macOS will now do is actually block this action, display an alert to the user, and only when the user clicks allow, and in some cases authenticates, will the action then be allowed. So obviously this is really good for users, but for hackers and malware, this is incredibly problematic. So now let's take a closer look at some of these security and privacy actions that will now generate such alerts. So first up, we have kernel extension loading. So since Mojave, kernel extensions have to be explicitly approved before they're allowed to load. So even if the attacker has root access and a kernel extension is signed, Apple will block this until the user clicks allow. And there's good reason for this. So I articulated an attack at DEF CON a few years ago, talking about how an attacker could bring a signed but vulnerable third-party kernel extension to a system they had infected, and then could load it, The system would allow it because it was signed, and then they could reliably exploit that. So they could just bring around this kernel extension, and even if the third party released a patch for that, as long as the attacker had a vulnerable version, they could always just bring it down. Now, this is not just a hypothetical attack. This was actually utilized by the Slingshot APT group, which targeted code signing enforcement on Linux. And one day I'll be able to talk about this a lot more. Now, we also have the mic and the webcam. Starting with Mojave, if any application, any malicious code, any legitimate application wants to access the mic or the webcam, this will be blocked by the system. An alert will be shown, and the user has to explicitly allow that or deny this. Again, this, from a security point of view, is a really good idea. There's a myriad of Mac malware that has utilized these devices to spy on users. So, for example, we have Hacking Team's backdoor, and also Fruitfly, which for over a decade was spying on Mac users, predominantly children, through the web. So, such a kudos to Apple for adding this extra layer of privacy. As highlighted in Apple's keynotes, recently they've added protection around what they consider sensitive or private user information. So these are things like accessing the user's contacts, the location, call records, SMS messages. So here, for example, we have some code, and if you execute this code to access the user's location, on previous versions of macOS, this would be able to execute no problems. But now this will be blocked, and an alert will be shown. Again, good for the user, bad for the attackers. Another new security feature in Mojave is various terminal commands will actually be blocked. So if you pop into a terminal and try to create a new cron job, surprisingly, Mojave will block that, alert the user, and then request explicit approval. This is news to me. Another new thing in Mojave is that AppleScript commands, which attempt to interact with other or remote processes, will be blocked. So a lot of adware, as we saw in previous presentations, would use AppleScript as a mechanism to, for example, inject code into the browser, but then would allow the malicious code to steal sessions, inject ads, etc., etc. So on the slide, we have some of this code from a piece of malware, or rather adware, that would inject into Chrome. Good news though on Mojave, because of Apple's new privacy and security mechanisms, this will now be generically blocked. So we've illustrated that basically everything worthwhile from a hacker's point of view will now be blocked on recent versions of macOS. Again, this will generate an alert that the user has to interact with. So what our goal is, as attackers, is to basically find a way to programmatically or synthetically interact with these alerts. And if we find such a way, the beauty of this approach is we can generically thwart all of these security and privacy attempts with a single click. Even though some of them are kind of unrelated and implemented in different ways, they all share a single component, and that is the user interface. So we can send synthetic clicks. We, for example, don't have to find a specific kex bypass or AppleScript. We can just click allow. Now, the power of synthetic events, synthetic clicks, have long been realized. So we'll now briefly look at some attacks and also how Apple has responded to these attacks. So first we have AppleScript. As I mentioned, AppleScript can be used to generate synthetic events. So all the way back in 2011, a piece of malware known as Devil Robber was dumping keychains to steal passwords. Now, when you access the keychain, this will display an alert, even all the way back in 2011, that basically would ask for user consent before allowing the application to access the keychain. What Devil Robber did, as we can see on the slide, is it would first request access to the keychain. This would generate an alert, and then would execute a secondary script, which would just continually try to click allow always via AppleScript. And at the time, there were no protections against these synthetic clicks, so this would get blocked. I'm going to give acknowledgement to North and Space for putting this out, because it was really nice of them to kind of point this out, that all the way back, even in 2011, these attacks were going on. We mentioned Fruitfly, which was the piece of Mac malware that would spy on Mac users. It also had the ability to generate synthetic clicks. This allowed the attacker to remotely interact with the UI. So he could, for example, disable certain security prompts or move and click the mouse. Now, of course, Apple realized they had to do something about this, and they did. In short, on recent versions of macOS, what they did was they filter out unauthorized clicks. So now if a random program tries to, say, move the mouse and generate a synthetic or programmatic click, the system will block that. Basically says, okay, this is not from the user, I'm going to ignore this. From a technical point of view, basically the way this is done is they check the process ID that is responsible for generating the system event. And if it's coming from the system, meaning it has pin 0, it will be allowed, because they assume this is coming from one of the mouse drivers or some system component. However, if it's a random application that is sending synthetic events, the system will filter that out and ignore the click. Now, of course, it was rather trivial to bypass this detection simply by finding ways to coerce or ask the system to generate arbitrary synthetic clicks for us. So I talked about this at DEF CON last year. It turns out that macOS supports a feature called mouse keys, which basically allows you to send keyboard events that the system then translates into mouse events. So it basically turns your keyboard into a mouse. Here's some mappings for this. So basically what I do is I turn on mouse keys, and then I send synthetic keyboard events, which are allowed. The system then translated those into mouse events, and then would deliver them to the target window. For example, where I was trying to click allow. Now the system would see and examine those events, but since they were coming from the system, because the system was doing the translation from the keyboard to the mouse, the system would allow this. So this gave me a way to interact with the UI pre-Mojave. Now, an even funnier, in my opinion, way to bypass these Apple's previous protections, was simply to generate 2 synthetic mouse down events. So normally when you click the mouse as a user, you click, which generates a mouse down, and then when you click and release, that will generate a mouse up event. So programmatically what I did, and this is pure accident, I just copied and pasted the mouse down event twice. The system kind of says, well, this doesn't really make sense. How can you generate 2 mouse down events? So it said, you know what, I'm going to help you out here. I'm going to take that second mouse down event, and I will translate it into a mouse up event for you, and then deliver it to you. So the mouse event would then go to the target window, which would be filtering the events and say, oh, this is coming from the system, I'm going to allow this. So to line the code, we could completely break all of Apple's defenses. Apple clearly got annoyed with me. He said, you know what, in Mojave, Patrick, take a hike. So what they basically did was twofold, which are both very strong approaches from a security point of view. First, they said, okay, we're going to block any and all AppleScript that tries to communicate with other remote processes, which is good because adware is also trying to use this technique as an injection mechanism. So now if your AppleScript tries to, for example, talk to Chrome or a browser, the system will just flat out block it and show a prompt that the user has to allow. Similarly, if you generate synthetic events, which we do via the CG or core graphic APIs, instead of trying to filter this, Apple just says, nah, we're going to flat out reject this. And not only do you have to click OK, you then have to go into the system preference pane, unlock it, put in your password, and explicitly improve this. So when I saw this, I said, okay, this seems like game over. Apple's basically shut the door and basically said, okay, we're not going to try to filter anything anymore. If you try any synthetic clicks, we're just going to completely block this. So, you know, game over. Well, not really. Unfortunately, if history has shown me anything, it's that, you know, Apple often struggles to get patches or fixes right. So now we're going to talk about a zero-day flaw in macOS that allows us to generate synthetic clicks, for example, mouse clicks, as a normal user, and we'll also show how to do this in an invisible manner. And this will allow us to do things like completely bypass all of Apple's recent local security and privacy mechanisms. So first, let's talk about some OS kernels. So behind the scenes, this is all handled by the TCC daemon. Some of the other talks mentioned this as well. And basically what happens is when a program tries to perform some action, for example, generating a synthetic click, the TCC daemon is what examines the application to determine if it's allowed. Because the user can go in and specifically add applications. For example, if you use Google Chrome and you use Google Hangouts, it's going to be access to your mic or your camera. So the first time you do this, there's going to be a pop-up. You're going to be like, yeah, I'm okay with Chrome using my camera and my webcam and my mic. This will then get added to system and privacy pane, which is then backed by the tcc.db. Next time you launch Chrome and try to join that same Hangout, what happens is TCCD will check the database and say, okay, yeah, Chrome was previously added by the user. That's okay. Chrome can now access that. This database file is protected by system integrity protection, so malware cannot go in and manually add applications, which is good. So the other day I was reading Howard Oakley's blog. Howard Oakley blogs a lot about Mac OS, a lot of really good stuff, so I recommend checking out his blog. And he was talking about TCCD and some changes in Mojave. And he had a very interesting line. He said that the rules there's, besides the main TCC database, there is a undocumented whitelist of applications. And it says the rules in this compatibility database grant access to protected functions for specific versions of apps with specific signatures. So as we can see on the slide, what conceptually happens is, say an application wants to access the mic, or generate a synthetic click, or access call records, any of those actions that are blocked. TCC first checks the TCC database, says, is this something the user previously explicitly allowed? If not, it checks this secondary undocumented whitelist and says, does the application match one of those applications in the whitelist? To me, that was intriguing. And that's all Howard said about this. So I want to say, okay, I want to dig more into this whitelist application database to see what it's all about. So step one was figuring out where this application database lives. So if we look at the TCC daemon, specifically its property list file, we can see it has a watch task for a file named allowapplications.plist. If we use something like Task Explorer, which can show us what files are opened by what applications, we can see that the TCC daemon has this file open, and no other process did. So this is likely this application whitelist. So let's take a peek at this file. So we can open the allow applications list.plist, and we can see that, yeah, it appears to be a list, a database, a property list, containing popular applications that are afforded the ability to perform actions that normally would generate alerts and be blocked. So for example, we can see there is VLC, which is a very popular media application. I have no idea why, but apparently it has the ability, or needs the ability, to generate synthetic events. So what Apple did behind the scenes in a fully undocumented manner is added an entry to this allowed applications list, basically saying that VLC can generate synthetic events. Now it's very important to know that besides the name of the application, they also have code signing information. So it's likely that they validate the application so that we can't subvert these. Also, this list is protected by system integrity protection. So far, so good. So put on my hacker hat, though, which is actually on all the time, I wondered, could I subvert one of these trusted applications? Because if I could, they are given the ability to perform these unauthorized actions without being blocked. Because if we can do that, in theory, we should be able to generate synthetic clicks and click allow on all these alert points. So let's take a closer look now at the validation logic within the TCC daemon to see how it treats these allowed applications. So after a bunch of reverse engineering, I found a method called matches code requirement data. This takes an access identity object and then the code signing information, or specifically the code signing requirement in Apple terms, of an application from the allowed application lists. If we look at strings in the code, we can see that if this method is successful, it basically says, okay, this allowed application is still validly signed, it hasn't been tampered with, so we will allow it to perform the action. Otherwise, if it detects that it's been subverted, for example, Patrick is trying to mess with it, it'll say, take a hike and not allow the application to perform the action. For example, generating the synthetic event. So again, so far so good. So if we take a closer look at this identity access class, we can see that when it's instantiated, it contains information about the application attempting the action. So we're going to stick with VLC again. We can see that at runtime, when VLC tries to perform an action, for example, a synthetic click, this access identity object contains all the information about the application, for example, the name and the path. If we dive into this method, the match code requirement data method, we can see it invokes a standard code signing API to verify, as I mentioned, that the application is still signed by the specific code signing requirement, which is extracted out of that allowed application list. So again, recall in that allowed application list is the name of the application, for example, VLC, and then all its code signing information. For example, the VLC developers code signing, team ID, etc., etc. Again, so far so good. Unfortunately, the devil is in the details. So as Apple's documentation states, the code signing APIs are controlled by flags. And the flags are passed into this API. So here we can see that the application verification is performed with flag number 7. And this is just a bitwise of 3 different values. Now I didn't recognize 7, it seemed a little odd, so I looked up what these values would correspond to. We can see at the bottom of the slide. So first we have check all architectures. This makes sense. Mach-O binaries can be fat, meaning they basically have a 32-bit and 64-bit chunk. So you probably want to validate all of them. The next 2 values for the flag make 0 sense. The next one is do not validate the executable, and then do not validate any resources. So since the do not validate executable and do not validate resources are not set, if we look at the code signing logic, it's basically going to ignore checking the executable or all its resources. So the only thing it's going to do is make sure that the application is signed by who they say it is. So the analogy I like, it's imagine you're at the airport and you book the ticket, you go up to passport control or checking in your gate, and you hold up a piece of paper with your name on it. And they check that the name matches what is on the booking, but they don't actually check that the paper is a valid passport or a driver's license. They basically say, yeah, this matches, so yeah, you're allowed on the plane. So, big fail. So, since the application is executable, nor its resources are validated, it's very trivial for us to subvert any of the applications on that allowed application whitelist to perform any of these disallowed actions, for example, generating synthetic clicks. So here's the steps we're basically going to do. Just choose any application from the allowed applications list. I choose VLC because I already had it on my system. You can obtain it, for example, download it. Then we're going to talk about how to subvert it. And then we're going to run the application, and it should be able to execute the subverted logic, which allows us to perform things like synthetic events. And in theory, even though the system is seeing these events, since the app validation is not implemented correctly, it will be allowed. So here's an example of us using, or rather abusing, VLC, which is one of the allowed applications. Now, VLC, this is not available in VLC at all. It's just one of the applications that Apple has given access to perform synthetic events. So VLC, it turns out, will load any plugin from its plugin directory. So what we can do is we can just drop a malicious plugin that's completely unsigned into the plugin directory and then execute VLC, and we can confirm that, yes, VLC loads our plugin. Again, this is not a flaw in VLC, it just says I will load plugins because this is what I do. Okay, next slide. Now, the real test is when our malicious plugin, which is now loaded in the process context of VLC, tries to perform some disallowed action, for example, generating a synthetic click, will that be allowed? Specifically, will the matches code requirement check return yes? Now, the answer, as we can see, the debugger is yes, because again, the flags that Apple passes to the code signing API says don't validate resources nor validate the executable. We haven't modified VLC's signature, although we have corrupted its application bundle, the signature is still valid. So as you can see on the slide, it still passes the validation. So here is a brief demo. What we're going to see is me basically loading a signed kernel extension, which will allow me to then export this. I did this on 10 macOS 10.14.3, but this still affects even the latest version of macOS. So the first thing I do is run the version. We're on 10.14.3. I'm going to show that system integrity protection is enabled. I'm going to do kexstat. I'm going to grep that rootkit.kex is not loaded. Nothing matches. And then I'm going to try to load my rootkit. It fails, basically saying the user has to approve, which makes sense. We're then going to run our attack, which in the background launches a subverted version of VLC invisibly. This then opens the system access prompt that has the allow button, and then we send a synthetic click to click allow. TCC is going to see this happening. It's going to go and validate the click. However, it sees that it comes from within VLC. VLC still validates due to the flaw in the flags they pass, and then this allows the rootkit to load. Now, you might be thinking, all right, Patrick, this is kind of neat, but if I'm sitting at my Mac and I open a Word document and all of a sudden there's a pop-up and the mouse moves and automatically clicks, like I know I'm going to be hacked. And yeah, I would too, like throw that Mac out the window, right? So what we need to do is we need to figure out a way to make this attack invisible so that we can generate and submit synthetic clicks, for example, to click on one of these access prompts without the user becoming aware. Very simple, trivial solution, and that's simply to perform this action when the screen is dimmed. Because when the screen is dim, it's going to be black, but the UI is still interactive. So what we can do is we can, for example, wait until the user is not active, and then very easy, we can programmatically dim the screen. We can then perform the action which will generate the pop-up, for example, trying to access the microphone or load the kernel extension. We then can send the synthetic click to the alert prompt, clicking allow. This will tell the system to allow that action, and action will be performed. We can also detect when the display is going to sleep, and we can slightly speed that up and dim it to 100% before it fully goes to sleep, perform the same attack. And then if the user is sitting there, they'll just see their screen dimming. So again, this is a very trivial way to pull off this attack invisibly so that the user is not aware of what you're doing, and it's interacting with the UI synthetically. Okay, so let's wrap this all up. First, I really want to re-stress the power of synthetic events. If you have the ability to programmatically interact with the UI, we can bypass basically all of Apple's local security and privacy mechanisms, all with just a single click. Also, and not to pick on Apple too much, because truth be told, I'm very fond of them. I don't know if that's reciprocated, but I'm okay with that. Their track record protecting this is not the best. So, for example, we tried to patch this in 2015, 2017, 2018, and 2019, here we are. macOS is still completely vulnerable to these kind of attacks. So as a Mac user, that's a little disheartening. I'm hoping this fix in this talk will inspire them to get the fix right this time. Also, I would be stoked if Apple spent maybe a little more time on security and less on marketing. They are really good at selling Macs, and they state things like people buy Macs because they're secure. And I think a lot of people at Apple believe this. Apple is doing a better job to improve this. But to me, it's rather disingenuous to get up on stage in front of millions of people and say, you buy our computers because they're very secure, when the reality is they're really not. I mean, this bug is trivial. I definitely have an ability to find these kind of bugs, but it would be naive or arrogant for me to think that there's not other people out here who have this same capability. So, there are other people looking for these type of bugs. I wish Apple would be a little more proactive about this. Now, I do want to end briefly by talking also how we can detect this kind of attack. When I talk about zero-day vulnerabilities, I realize I'm being part of the problem, but if we talk about detections, hopefully part of the solution as well. So let's briefly talk about how you can generically detect these kind of attacks. So first up, it's actually pretty easy to detect synthetic clicks. What you can do is, on the system, you can register an event tap, which will ensure that anytime a mouse click is generated, you can observe this action and basically examine the click. And that makes it really easy because the operating system will set a flag if the mouse click was synthetically generated. And it will also tell you the PID of the process that was responsible for generating the synthetic click. So here's code to do it, just a few lines of code. We generate an event tap. As I mentioned, every time a mouse click is generated, our callback will be invoked, and we can then get the state of the click, which will be set to 0 if it's a synthetic click. So as I mentioned, I work at Digital Security, and even since last year, we track synthetic clicks because this is not something we see on a normal system. So this means that even with no a priori knowledge of this attack, we were able to detect this. And I don't mean this to sound like a sales pitch. I'm just saying, these attacks can also be detected fairly easily. So again, if you're tracking synthetic clicks and alerting on those, you could detect this and any of the other synthetic-based attacks that I've talked about. All right, so thanks again for attending my talk. Also, on a personal note, I want to thank the Friends of Objective-C, who are also sponsors of this wonderful conference. If you have any questions, come up and chat with me, or shoot me an email at patrick@digitalsecurity.com. So that is a wrap. Are there any questions? Somebody's going to ask something. Mike? Okay, well, I'm not on mic duty, so.
Yeah, good question. Looking through the, not that I looked through myself, but you probably have, the list of compatible apps, did any of them actually have, were any of those sort of apps would load plugins from outside their own bundle so that they wouldn't even need to, and even if Apple fixed the problem by changing the flags, anyone that just came along and loaded a plugin that was a valid plugin, but you see I'm coming.
Yeah, I'm thinking about that. Actually, let's take a look and see. Yeah. In theory, if they are, if they're validating it at runtime, maybe they would see that. Yeah, I guess it's a good point. If any of the applications are loading external plugins, the app bundle will still be allowed. Generally, that's not something that applications do. I mean, if they do load external plugins, they will be Apple-trusted plugins. But, for example, if the application has a dial-in hijack capability and is looking in a user-controlled location first, before the system location that's outside the app bundle, that would still work. So that's a great thing. We'll see how they fix it.
Did you, since you now able to see what apps are doing, did you ever figure out why VLC was creating mass events?
Yeah, I have no idea. Yeah, that's a good question. I mean, I looked at some of the apps in your video games, and maybe I had a tutorial that needed to move the mouse, but I have no idea why VLC has to have the ability to generate synthetic events.
So I assume the answer is no, but when you are dimming the screen or waiting for detecting when it's about to sleep, I assume the synthetic mouse click does not wake or bring it back out of sleep.
Correct. So actually, when the display is in sleep mode, the UI is not interactive. When the screensaver is on and you send a synthetic event, it wakes up or pulls it out of. So that's why dimming is the one and best solution. Because when the screen is dimmed to 100%, it's fully black, and any mouse clicks that you generated will be delivered to the window that's there, even if you can't see them, and it won't unset the dimming. And of course, you can also undim it when you're done with the attack. But again, it'd be kind of weird if you're working on a Word document and all of a sudden the screen dims, like exactly. Okay, I didn't see a synthetic click, but that's odd. So what I do in the proof of concept is I wait until the user is not active for 15 minutes, or actually I kind of slip screen the display going to sleep, because Apple takes about 2 seconds. They dim it first over 2 seconds and then put the display to sleep fully. So what I do is I get an alert when the screen starts to dim. I speed up the dimming process so it fully dims in 1 second. Then I have 1 second, which is more than enough time to perform an action, click allow, and then allow the screen to fully go to sleep. So in that way, the user would likely never know because the screen is already legitimately going to sleep. So excellent question though. Any others?
So in your personal opinion, if Apple used their own hooks to alert you when a synthetic click occurred, just like you can kind of write a tool,
Sure.
you think users would recognize that click shouldn't have really happened, and if it popped up and said, "Hey, VLC is trying to click something," I didn't install VLC.
Yeah, no, that's a great point. So those of us who write security tools, we kind of have an advantage because, we can alert the users and hopefully do those kind of things. Apple generally doesn't like to bother the user. So I was even very surprised that in Mojave, they now have all these new pop-ups. And as many of us can attest to that write legitimate security tools, these also cause problems for legitimate security tools. We're going to talk to Thomas Reed about kernel loading extension. So this is something that Apple has added, the explicit requirement that users must explicitly approve kernel extensions. So if you're building a consumer security product that loads a kernel extension, for example, a firewall or an antivirus product, you now have to tell the users, don't open this and click allow. As I've shown you, since its inception, this has never been secure, meaning the bad guys have always had a way to circumvent this. However, us security researchers who develop security tools have had to play by Apple rules, right? We can't build 0 days into our tools. I mean, that would just be bad form. I'm tempted, I'm not gonna lie. So we have to struggle with this, whereas hackers just, laugh all the way to the bank. So we're not to pick on Apple too much, but this is sometimes problematic because I don't think the security impacts sometimes weigh the downsides, especially third-party security developers. So that's kind of frustrating. But yeah, just to answer your question, I think that's why Apple went the route and said, look, we're just going to block all synthetic events. But then they didn't. If they would have, we wouldn't be having this discussion. Or if they would have done the code scanning checks correct. And again, if they would have audited this code, they would have, anyone with a security mindset who looked at this code would have immediately realized this. So again, not to take away from this bug, because it's kind of neat, but once you see it from a security mindset, it's blaringly obvious. So I would also beg Apple to audit stuff a little better, or have people with security backgrounds look at the code before shipping it, especially if they're going to go up on stage and tell everyone about this great feature that is fully broken. That's how I really feel. Okay.
Sorry, last quick question.
No worries.
What is the actual legitimate use case for synthetic events? Why would there be a synthetic mouse event?
Yeah, so that's a great question. So the two I know are accessibility software. So that's a really important one because obviously users with disabilities should be able to interact. And then the other cases are things like remote software. So things like remote desktop. I believe that those events come to the system as synthetic events because they essentially are programmatically generated on the remote system and then delivered. So, that one slide that showed Apple kind of failing to patch that, well, the reason they kind of struggle with this is because there are legitimate cases. Us developing security tools, we still probably want to always report those events so we can say, okay, this is a legitimate sysadmin who's coming in via VLC or something and adminning the system, and then we can look at that closer. But Apple can't really make such a draconian decision because, as Jared pointed out, the average user is just going to be confused, and it's going to impact Apple's wonderful experience.